Pionier Precision Integrated Optics Near-Infrared Imaging Experiment. Instrument for Very Large Telescope Interferometry. Built by IPIG Institute. Jan Philip Berger, who was one of the PIs of Pioneer, tells us that the scientific motivation when designing the instrument was that we needed to somehow increase the angular resolution, so that we would be able to zoom in the internal part of the protoplanetary disk. This instrument was designed to combine for the first time the 4 VLTI telescopes, with the UTs, the unit telescope, and the small auxiliary telescopes. The beams of light collected by telescopes travel through an optical train, made up of many mirrors, with the primary mirror spanning 8.2 meters. Along the way, the differences in the travel distances due to the Earth rotation and the distance between the telescopes are compensated by the delay lines to make the beams reach the instrument in phase, in addition to correcting the longitudinal effect of the mechanical vibrations in the light's path. This is called the fringe tracking. At the entrance of the instrument, there is a dichroic for each beam, which separates the light, sending a part of this to iris, which is a guiding system. The H-band light goes to the instrument. The beams are sent through periscopes that raise the light to the instrument located in the upper part of the VLTI laboratory. Each beam is sent to the instrument to produce the science data. For the science mode, the beams are sent to the piezo modulator to scan the optical delay path of each beam. Then each beam is directed to a tip tilt correction mirror moved by piezoelectric actuators controlled by iris during the observations and calibrated every day using an internal halogen source. Then, 4 shutters are opened to send the beams through the lithium niobate windows, to correct the variation of birefringence of the optical fibers. It's measured and balanced by the rotation of the windows, around their vertical axis during the calibrations taken during the day using picomotors. This adjustment is kept for the night. After passing through the lithium niobate windows, the beams travel the path to the integrated optics, being injected first in monomode optical fibers by off-axis parabolas to perform a spatial filtering, to remove the intensity fluctuation due to turbulence effect. The integrated optics combine the beams of the 4 telescopes, to make interference for all the 6 baselines simultaneously. In one observation mode, a grism can be inserted to disperse the light of the 24 outputs over 6 pixels to observe the fringes in 6 different wavelengths. The piezo scanning and modulation will allow to find the fringes and determine amplitude, phase and visibility on each of the baselines as shown by the RTD scope. Using the lithium niobate picomotors, we can co-phase both polarizations, performing the overlap of the red and green curves. This will allow to reach the maximum contrast of the fringes with the maximum flux using the single grism. On this picture you can see an arrangement of 3 integrated optics components. The middle one is illuminated by a laser on a bench. On this picture you can see the complete scientific detector with a pulse tube cooling system. On the left, the optical arrangement re-imaging the output of the integrated optic component. Fantastic science results. Since 2010, the instrument has been used for different scientific demonstrations. On the top left, what is called a post-AGB binary star with the burning gain disks. Here you can see what is called a vampire star, interacting binary. The surface of a dying star, which looks like the Sun but in 5 billion years. And recently, results came up, showing images of the inner part of protoplanetary disks, with an angular resolution between 10 and 20 times better than ALMA or sphere.